All right, welcome everybody to today's webinar by the International Solar Energy Society, ICES. We are very pleased to have all of you here, and we are especially happy to welcome our speakers and you, the audience, on this webinar. We are very much looking forward to the session and to learning all about the latest edition of the PVPS Task 16 Handbook. My name is Arabella. I am the Communications and Outreach Officer here at the ICES HQ in Freiburg, Germany, and I will give you a short introduction into ICES and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society ICES is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ICES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ICES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ICES, and you can find out more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings, such as today's, in the ICES webinar archive. ICES members can also get discounts and even free registrations to ICES events and partner events. Every month, ICES publishes a newsletter for our members where you can follow our progress and share your news. Members can also subscribe to our academic journal, Solar Energy, our flagship publication at a reduced price. And in the ICES online bookshop, ICES members qualify for reduced prices on the different publications. So we welcome those who are not yet members to join today to support our work. For those who are already a member, we thank you. As a special benefit to all attendees of today's webinar, we are very happy to offer a special discount when signing up as an ICES member. All attendees of this webinar will receive a 20% discount code as a follow-up to the webinar over the next few days. This special offer will only be valid for about 2 weeks, so sign up quickly and join ICES and the global solar community. Now for some brief information on the Q&A session before we start. For the Q&A session, we invite you to send in your questions, and we're looking forward to your participation. When sending in your question, please write who the question is for and keep it short and precise. You can start sending in your question anytime throughout the webinar. I am now happy to introduce you to our moderator for today, Jan Remund. He's the project lead of the Global Solar Radiation Database Metronome, and he's the operating agent of the IEA PVPS Task 16 since 2017. Now, I'm happy to hand over to Jan. Jan, thank you for joining us. The floor is yours.
Thank you, Arabella, and welcome everybody. I'm happy that you joined our webinar. I just have to start my screen now. Okay, now I'm starting the introduction. I will tell you only a few minutes what's all about the IEA Task PVPS Task 16. My name is Jan Remund. I'm working at Meteortest, and I'm the operating agent since 2017. What is the IEA PVPS? So the IEA is an autonomous body within the OECD, and PVPS is one of the so-called technology collaboration program, which tries to enhance the role of PV in the energy transition. We are at the moment partners of 18 countries based on universities, research organizations, med services, and service providers. Here you can see a logo wall of the institutions, at the moment 49 and 89 experts. It's not covering the full world. It's as South America and from Africa, south of Sahara and Asia. Up to now, there are no partners. But we would welcome, of course, if such would be available. Why a solar task? Solar resources are the fuel of PV, CSP, and solar thermal energy. Big PV and high penetration need high quality of meteorological information. We deliver added values like independent benchmark, state-of-the-art descriptions. Finally, we lower the uncertainties in the resource assessments, which lowers the cost of implementation, which leads to the building of more PV. The first phase of the task was between 2017 and 2020, the handbook which is presented today is the main outcome. The second phase started last year and will go on for 3 years. We are organized in 4 subtasks. One is about measurements and models, led by Manojit Sengupta and Stefan Wilbert. Both of them will be available today as well. Subtask 2 is about enhanced data and bankable products, led by Philippe Blon of MinParitech. Subtask 3 is about solar forecasting techniques, led by Elke Lorenz and Carmen Köhler. Elke is present today as well. And subtask 4 is about dissemination and outreach, led by myself. This update of the Solar Resource Handbook is one of the results of the main dissemination results of our task. We currently make regularly webinars, workshops, and have also started to have an online code archive. That's all from my side at the moment. I'm happy to hear the news about the handbook, which is really a great work. And I'm giving now the word to Manojit Sengupta. First, I'll tell you some what he's doing. So Manojit Sengupta is currently the chief scientist in predictive analysis and at NREL, and leads the research and areas of solar resource assessment, solar forecasting, and PV variability. He has 25 years of experience in atmospheric modeling, assimilation, and observational analysis, and he is an expert in remote sensing, forecasting, analysis of clouds, and solar radiation. He is also the deputy lead of Task 16. So please, Manojit, the floor is yours, also virtually.
Sure. Thanks, Jan. Welcome, everyone. You've just heard from Jan about our IEA PVPS task. My name is Manojit, and I'm going to quickly provide an overview of the best practice handbook. Given that there are so many experts in this task, dissemination is a big piece of the work we do. This handbook is our primary mode of dissemination of all the work all the knowledge we have within this task. So this is the 3rd edition of the Best Practices Handbook. The handbook is updated approximately every 3 years, with any new knowledge which is produced through our collaborations is included in the newest edition. The previous 2 editions, first and second, were produced through the solar heating and cooling task. The 3rd edition now is under the PVPS task. So let's quickly jump into what's there in this handbook. For those who've already seen the previous versions, they know that there are so many authors on the handbook, experts writing various chapters. Again, this edition has 10 chapters with 41 authors and for representing 14 countries. So they're all listed here, and it's a big shout out to everybody for their time and effort to make this handbook a success. So quickly introducing the chapters. There are 10 chapters, like I mentioned. Chapter 1 talks about why solar research data are important to solar power. It just contains a short summary of what is contained in each chapter. Chapter 2 provides an overview of solar radiation resource, basic concepts and terms which would be needed if you have no knowledge of what solar radiation is in theoretical sense. So it is essential for understanding the subsequent chapters. Chapter 3 it talks about how to measure solar radiation and relevant atmospheric parameters. It describes the state of the art in measuring solar radiation and offers methods and protocols to produce a quality assessed data set. Chapter 4, it talks about modeling solar radiation and the current practices, focuses on modeling solar radiation, and provides an understanding of current practices for calculating solar radiation using various inputs, mainly though the satellite-based measurements as inputs are covered in detail here. The next chapter is chapter 5, which is further relevant meteorological parameters. And as you can see, I have the ones which are marked in red here. We're going to have more details about these chapters because within this handbook, the 3rd edition, these are the chapters which have either are new or have been heavily updated based on on work which has been done in the last 3 years. So chapter 5, chapter 7, and chapter 8, and on this slide, you're going to hear more details about it, about these chapters going forward. So in chapter 5, what we're doing is we're introducing further relevant meteorological parameters because it introduces measurement sources and models for obtaining meteorological and solar parameters that are required for improved accuracy in solar modeling. Essentially, not just broadband solar radiation like GHI and DNI, but other meteorological parameters which are needed for solar modeling as well as spectral radiation. So anyway, this will be discussed in detail going forward. Then we have a chapter on solar resource data, which presents several examples of solar resource data sets which are available, and this chapter has been updated with most recent links to most recent data sets. Chapter 7, Measurement and Model Uncertainty, provides an understanding of data quality assessment and how to estimate and interpret uncertainty in both measured and modeled data sets. Chapter 8 is on forecasting solar radiation. As most of you know, that this is a fast evolving topic, so there's been an update on this, and you're going to hear more about this, about forecasting pretty soon. Chapter 9 is applying solar resource data to solar energy projects, and it recommends best practices to apply the solar data sets we talked about in the previous chapters. And chapter 10, of course, talks about future work, outstanding problems, which will require collaborations to solve. So those are, it's just the quick overview of the chapters. Just to highlight, a summary highlight of what's in the handbook. The new instrument classification standard, ISO 9662, is included. We have updated radiation models, including fast models, spectral radiation and broadband radiation. That's been included. There's a new chapter, like I mentioned, on further relevant meteorological parameters, including aerosols, temperature, snow, UV, radiation, and surface albedo. The inventory of available datasets sources has been updated. There's a chapter on measurement and modeling uncertainty and new information on automated data quality tests. Like I mentioned, that we have an update to the forecasting, and you're going to hear more about it. And then finally, the chapter on applying solar resource data has been thoroughly revamped. You're going to hear about that too. So thank you to all our reviewers. This makes our handbook much better. Our reviewers have done an excellent job. We really thank them for their time. And without much ado, I will hand this over to our next speaker. And our next speaker here is Dr. Stefan Wilbert. Dr. Wilbert leads the research group in solar energy meteorology at DLR. DLR's Institute of Solar Research in Almeria, Spain. He has 15 years of experience in the field of meteorological measurements and models for solar energy applications, forecasting, and solar power plant simulation. Dr. Wilbert acts as a subtask lead and activity lead in the International Energy Agency's PV Power Systems task on solar resource and forecasting. Stefan, the floor is yours.
Thank you, Manajit. So this presentation is about further relevant meteorological parameters. I present this new chapter on behalf of all the authors of this new text. I was happy here to count on experts on each of the parameters that are described in this section, and it was really a good team effort. The overview of the new chapter and also of my presentation is shown here. So this chapter introduces the several meteorological parameters that are required for solar energy besides the broadband irradiance. The parameters that we present are wind, wind speed, wind gust, and wind direction, the ambient temperature and relative humidity, atmospheric pressure, precipitation, aerosols and water vapor, spectral irradiance, UV irradiance, soiling, circumsolar radiation, the beam attenuation between heliostats and the receivers of tower plants, and the surface albedo. For each of these parameters, we provide definitions, then explain how they are, what is their effect on solar energy. We provide measurement options and described modeled data sources. There's lots of references here in this chapter. This is very important because the chapter is quite short, only 30 pages for all these different parameters. So we really only give a rough description of each parameter, but provide you with the links to other texts which give detailed informations. I will today only present 3 parameters: spectral irradiance, soiling, and surface albedo, as 15 minutes are too short to talk about all these different parameters. And I will now start with the spectral irradiance. The spectral irradiance spectra can vary strongly with solar position and atmospheric conditions. An example is shown here on the left-hand side with a spectral direct normal irradiance as a function of the wavelengths. We see different spectra with very different shapes for different times of the day and different air masses. And now some solar energy systems and also some radiometers only use a part of the solar spectrum. This is shown here on the right-hand side, where we have the normalized responsivity of different PV technologies and a silicon photodiode pyranometer as a function of the wavelengths. Now, if you have yield estimations based on wrong assumptions related to the spectrum, this can lead to quite serious errors. Even for crystalline silicon modules, yearly yield estimations can be wrong by between -5 and +2%. And this happens at times because the data availability for spectral irradiance is not very good. This is the case because spectroradiometers are quite expensive. They require complex laboratory calibration, and some instruments are really difficult to maintain. For a wide spectral range, you need several detectors. Silicon sensors are not usable beyond about 1100 nanometers, and therefore a nice measurement system looks like this one here from CMAT's Plataforma Solar de Almería. There are CCD error spectroradiometers from the WISER system, 2 instruments for global horizontal irradiance, and 2 instruments for direct normal irradiance, both covering 300 to 1700 nanometers. Such systems are really expensive and therefore limited to research stations. An option to provide further measurements of solar spectra could be to combine measurements at a limited wavelength range and combine it with modeling. There are several modeling options available. For example, the SMART software for clear sky spectra, or FARMS or LibRadRun for all sky spectra. There are some data sets available, for example, TMY spec, and there's also more data, spectral data in the NSRDB. And CMSAF also provides satellite-based spectral irradiance data. In our chapter, we also refer to the different standards on terrestrial solar spectra from ASTM, IEC, ISO, and CIE. On the right-hand side here, we see an example from ISO. That's the spectral irradiance, the global tilted irradiance spectra at 37° tilt that are defined as subordinate spectra from ISO. These are for different atmospheric conditions and altitudes. You can again see the different shape of these spectra occurring due to the different atmospheric composition. As I mentioned earlier, there's a further section on UV irradiance, which is important for aging, for example. With that, I come to soiling. The soiling ratio is the efficiency of the actual system that might be dirty divided by the efficiency of the clean system. This is a strongly relevant parameter for all solar energy technologies. Even in Germany, the observed soiling ratios can be below 50%, and also the average loss is quite significant with about 3%. Using the soiling ratio, you can optimize your cleaning schedule, which is an important thing. And also, if there are other technical problems, you need soiling ratios in order to separate these technical problems from the soiling. For PV, soiling can be measured with different measurement options. One can compare a reference module to the test model. One is cleaned, the other one is left dirty. The same can also be done with reference cells. Here are two pairs of reference cells, one with smooth cover class and another one with textured cover class. This kind of measurement requires that you clean the clean reference device, and this is a complication in practice. And there's also another issue. If you work with PV modules that consists of different cells, so not like in this case where we have the SIMT film technology, but if you have different cells inside the module, the inhomogeneous soiling can be an issue if you work with short circuit current based measurements. So in this case, an IV curve would be required or helpful. There are also soiling sensors. For example, active light sources can be used in this dust IQ sensor. There's also a mass sensor on the market that uses a microscope to visualize particles on the glass surface and then derives the soiling. And there are other image-based techniques in the literature. One can also measure the efficiency change due to cleaning. However, this is quite complicated because it involves two quite uncertain efficiency measurements. For CSP, this looks different. Also here, the effect of soiling is much more pronounced. CSP is affected about 10 times more by soiling than PV because of the small CSP acceptance angles. Soiling basically means scattering, and the scattering is much less important for PV than for CSP. On top of that, in CSP systems, there are also absorbers, envelope tubes of absorbers or other entrance windows that can be affected by soiling. So this is another add-on of the soiling effect there. There are different measurement options. I list here some for reflectance. For example, the TRAX system here, the TRAX paralleliometer looks at the sun via the sample mirror, and then this signal is compared to the direct normal irradiance from the main paralleliometer. There's also other systems around, for example, the AVOS systems, or one can use handheld reflectometers, although this latter option is very time-consuming and therefore expensive. Soiling can also be modeled. There are simple models around. There are also more complex models around. Inputs for complex models are aerosol concentration. This is very important. Precipitation, this is also very important. And then further parameters like 3D wind, humidity, temperature, dew can be used. Also the soil properties next to the power plant and solar system surface properties might be considered. The output of soiling models is the change of the soiling ratio that can then be used to model the soiling ratio of the solar field. Now I come to the albedo. The albedo is defined as the reflected horizontal irradiance divided by the global horizontal irradiance. It's very relevant for all non-concentrating tilted systems because there is a radiation contribution from the ground. It is especially relevant for bifacial PV, as here we also have the backside plane of error irradiance, and this can be modeled using albedo, direct and diffuse irradiance. These models can then be ray tracing models or sky view factor models. However, it's also important to mention that also all other solar energy systems somehow require albedo, because the modeling of surface irradiance also requires the albedo information. The measurement involves two pyranometers as shown in the sketch here. The height of these pyranometers above the ground is very important. For PV systems, the height is recommended to be between 1.5 and 2 meters. We summarize the different options and recommendations from the relevant standards from ISO and IEC in our section on albedo. But the height is very different if you want to compare your ground-based albedo with spaceborne observations of the albedo. Here, heights of 10 meters or more are recommended. For example, in the photo here, we see the windmast with pyranometers on top of it, looking downwards at Zermatt's Plataforma Solar de Almería. The albedo is highly variable, both spatially and temporally. Spatially, this is well known. If you look down from a mountain, you see all these different colors. The temporal variation is maybe less known, but it's shown here in the plot. We have the albedo on the left y-axis, the irradiance on the right y-axis, and the daylight time on the x-axis. We see 2 days, a cloudy day. Here the albedo changes, but not very much, only in the morning and in the evening. And for a clear sky day, there's a quite pronounced change of the albedo. This can be understood better by looking at this equation. Here we have the reflected horizontal irradiance. It is calculated as the product of the black sky albedo and the direct horizontal irradiance, plus the product of the white sky albedo and the diffuse horizontal irradiance. The black sky albedo is the directional hemispherical reflectance for direct irradiance, and the white sky albedo is the reflectance under isotropic diffuse illumination. There are different data sources. For example, MODIS, ERA5, MinParitech, and also SEMSAF provide albedo data. Here on the right-hand side, we can also see another example of the temporal variability of the albedo. The graph shows daily average albedo plotted versus the time for several years. And one can see here lots of changes, seasonal changes, typically lower albedo in autumn, spikes at time here in winter. But one can also see that the albedo is not the same every year. This additional interannual variability is a further complication that has to be considered. With this, I already come to the end of my presentation. I hope I could give you a good overview of this new chapter, and I'm open for questions afterwards in the session. Thank you.
Sure. Thanks, Stefan. Our next speaker is Aaron Hapte from NREL. So Aaron Hapte is a research scientist at the National Renewable Energy Lab in the Sensing and Predictive Analytics Group. For the past 10 years, he has been working on research and development in solar and atmospheric radiation measurements, modeling, data quality assessment, uncertainty quantification, and standards and best practices development. He's the chair of the ISO TC 180 subcommittee, and on the subcommittee one, he's on climate and measurement and data. Furthermore, he is the chairman of ASTM International Standards Subcommittee on Radiometry and vice chair of ASTM International Committee on solar, geothermal, and other alternative energy sources. So without much ado, Aaron, the floor is yours.
And so I will be presenting an overview of Chapter 7, Solar Irradiance Uncertainty and Data Quality Assessment. And the collaborators for this chapter are Darren Myers, Steve Wilcox, Stephen Wilbert, Chris Gaymart, Manoj Singh Gupta, Tom Stoffel, Frank Vignola, and Marcel Suri. And thank you to all the co-authors of this chapter. So I will give an overview of the chapter 7. This chapter discussed the uncertainties associated with measured and modeled solar resource data along with data quality assessment. And this is important because it provides a basis to assess confidence in the predicted output of PV systems. And it's a key factor also when determining the bankability of the solar project. And there are multiple sections in this chapter, but the presentation will focus only the uncertainty in irradiance measurement, uncertainty in modeled irradiance, and data quality assessment. And all the other sections that are not presented here are kind of revolve around this three sections. So solar resource measurement uncertainty. And as we know, uncertainty is a way to specify confidence in the data. It is important to determine the uncertainty using a standard methodology to provide confidence in the result that can be traced, for example, by a set of equations. So in this case, the guide to the expression of uncertainty in measurement, the GAM method, is used as an example here to determine uncertainty in measurement. And as you can see, 6 steps are followed using the GAM method. The first step is to define the mathematical equation, measurement equation, that describes the relationship between the dependent and independent variables. If it is measurement, the sensor voltage and the responsivity or calibration factor would be independent variables, and the desired output would be the irradiance. In step 2, would be defining the source of uncertainty. They relate to the measurement equation that was defined in step 1. Some common sources of uncertainty associated with radiometers are, if it is measurement, then it would be calibration, directional response, spectral response, and so on. And we have to understand the effect of these sources to each variable in the measurement equation. For example, calibration uncertainty is directly related to the responsivity or calibration factor. So when you do the calculation, you have to assign that to the each variable that affects. In step 3 would be an individual standard uncertainty for each variable in the measurement equation. It would be calculated using either a statistical method, which is a type A uncertainty method or component, which is defined in the GAM method. That could be, for example, standard deviation, and the other method is type B uncertainty component, such as manufacturer's specification or calibration reports that you get from manufacturers, and experimental or your own experience could be tied to type B uncertainty. And then step 4 is to combine the various uncertainty. In the next step in this, in 4, what you need to do is the uncertainty must be weighted. The GAM method does this by calculating the sensitivity coefficient of the variables in measurement equation. And this is done using a partial derivative of that measurement equation that was described in step 1. These coefficients affect the contribution of each input factors to the combined uncertainty of the irradiance value. Then on step 5 is combining this 3 and 4 using the propagation of error formula, that is a square root sum of squares method. It is applicable to both type A and type B source of uncertainty. And then at last, the expanded uncertainty is calculated using by multiplying the combined uncertainty in step 5 by the coverage factor, typically by applying student's T analysis to determine the appropriate value of K. In this case, it would be 95 confidence interval, and the K coverage factor would be 1.96. And this flowchart is to show how the calibration traceability and also accumulation of uncertainty for both pyrheliometers and pyranometers. And as you can see from this, as we go from top to bottom, when we start from World Radiometric Reference, WRR, all the way to field deployment, the uncertainty values increases. So that is the takeaway message from this slide. So this table is also showing like how after applying the GAM procedure, what kind of uncertainty you get for pyrheliometers and pyranometers. This table summarizes the estimated uncertainty that are typically found in practice, and the takeaway message from this table that we included in the handbook is not all the sources of uncertainty doesn't affect the overall uncertainty the same way. And what I mean by that is, for example, calibration in this case is about 3%. If you see aging per year is 0.2, so calibration has more impact in the overall uncertainty compared to the aging per year. And also, the other thing is thermopile pyranometers versus photodiode pyranometers. The uncertainty is kind of different or larger when you talk about photodiode sensors. So in the next few slides, I'm going to talk about modal uncertainty. And with that, so this is quantification of modal uncertainty. So to improve model data integrity, a comprehensive representation of modal uncertainty method is required. However, it is important to describe the difference between model and measurement uncertainty that I talked previously. Modal uncertainty is affected by two things. One is the model inefficiency or model limitation. And the second one is the input parameters uncertainty, which propagates to the model. So how do we quantify this uncertainty errors or uncertainties? So the error propagation effects can be evaluated by analyzing the model sensitivity to variations in the inputs, but you have to have a known uncertainty of those inputs. So this is difficult to do. So in practice, most data sets are compared to ground measurements. One thing to note is when you compare to ground measurement is you have to include the uncertainty of the ground measurement to the overall uncertainty of the model. So what are the current approaches to quantify overall model uncertainty? So this is many studies discussed like quantification methods aimed at comprehensive representation of model uncertainty using different interpretation of the GAM method. And in the absence of consensus methodology, there is no consensus at this moment. NREL developed a way to include this source of uncertainty to derive the expanded uncertainty at the 95 confidence interval, representing or with coverage factor 1.96. But using this equation. So as you can see, U measure is the measurement uncertainty from the ground measurement that you use to evaluate the model. And the bias uncertainty, this is mean bias error, and then you have RMSE. All these errors are treated as a type B uncertainty here to follow the GAM method. So, but the issue here is this is kind of a conservative approach because we know the RMSE includes the bias error in it, so there is a double counting issue here. So the authors of this handbook are working to come up with a better method to investigate a better uncertainty quantification method for models. But using the NRL method, you can see this is our different time horizons. On the x-axis are the stations for 7 stations, NOAA SURFRAD stations. And the hourly is higher, and the annual uncertainty is lower, sometimes close to the ground measurement, which is the red line. This red line is the uncertainty that is estimated for the ground measurement. So Solar GIS also implemented a similar approach, slightly different than the NREL. They included the interannual variability in the estimation of the overall uncertainty. So I think the main takeaway is how do we kind of come up with a consensus method to show model uncertainty is still a question. So in the next few slides, I'm going to talk about automated data quality evaluation methods. With that, I am going to present only one of the methods. We have 2 methods described in the handbook right now, which is the NREL CRQC method, and also there is the ARM atmospheric radiation measurement network, which is a QC-RAD. But I'm going to present only the NREL method here. So data quality assessment is a method by which data quality can be judged based on a set of criteria. Several particular errors of meteorological data can be detected by automatic screening algorithms. And depending on the available data, CRQC performs 1 or 2 or 3 element tests, which each with progressively narrow for acceptability. And the 1 element test is defined by a range of acceptable values between minimum and maximum values of the clearness indexes for KT is for a clearness index for GHI, KD is a clearness index for diffuse, and KN is clearness index for direct. And that is based on the 3 air mass regions, which is on the table low, medium, and high, and for each month. And for the 2 element test, software compares against a range of sets specific acceptable values defined by empirically derived boundaries. The boundaries are called Gompertz curves. So these are developed for each station using multi-year ground measurement data sets. So any new data will be compared to this envelope here. And if it fits, if they fall in within the range or outside, they get a different flagging values. And the 3 element tests are performed also using a range of acceptable values using the closure test, where it is KT equals to KD plus KN. Clearness index of GHI equals to clearness index of diffuse plus clearness index of direct. And that is the takeaway message from this slide. And we have a publication here, this link for this specific software. And the other thing is the CRQC flagging scheme provides information about the magnitude of the error, the direction of the error, high or low, and what test, 1, 2, or 3 element test that I described earlier, and produce a flagging also. So you will get like 4 of these types of cylinder plots. This is, for example, for KT, and there are cylinder plots for KN and also for KD. And there is an additional cylinder plot for the flagging. So the purpose of that is you can compare errors can be instantly, like you can see them, and they can be correlated also with the irradiance value, the errors. And the 3 components, which is KT, KD, and KN, can be viewed in context within each other. And as you can see here, days of the month is on the y-axis and hours of the day are on the x-axis. with that, I complete my presentation. Thank you for listening, and I look forward for the questions later on. Thank you.
Thank you, Aaron, for a nice presentation. Our next presenter today is Dr. Elke Lawrence. Dr. Elke Lawrence is a physicist and heads the Energy Meteorology Group at Fraunhofer ISA, and she's leading this group since 2016. Previously, she worked in the Solar Energy Meteorology Group at the University of Oldenburg for 15 years. And she's starting with a PhD on satellite-based solar irradiance forecasting, and then ending up heading the group from 2011 to 2016. Her research focuses on PV power forecasting and solar irradiance modeling. She's managed many national and international research projects, and she leads the subtask on solar irradiance forecasting and the IEA task on solar resource assessment. Without much ado, the floor is yours, Elke. Please go ahead. And we can see your screen. Thank you.
Okay. So thank you for the introduction, Manajit. And I would like to present you Chapter 8, Forecasting Solar Radiation and PV Power of this handbook. Yeah, and many colleagues of the IEA task have contributed to this chapter, so thank you to all of the many co-authors here. Yeah, I would like to start with a short overview of the chapter, which is also the outline of my presentation today. So the chapter starts with an introduction. Then we give an overview of empirical and physical solar irradiance forecasting methods, followed by irradiance forecasting with statistical and machine learning methods. Then the next section addresses how these irradiance forecasts are converted to PV power forecasts, and a special forecast here, focus here is on regional PV power forecasting and upscaling. Yeah. After this methods section, this is followed by a section on the evaluation of irradiance and PV power forecasting, and a section on probabilistic solar forecasting, and the section is finalized with summary and some recommendations of solar irradiance forecasting. Yeah, I would like to start with the empirical and physical solar irradiance forecasting methods. For empirical methods, we have irradiance forecasting with cloud motion vectors. So there is two types of these forecasts: forecast based on all ground-based all-sky imagers and satellite-based forecasts. And yeah, for physical solar forecasting model is numerical weather prediction models. So in this section, we give an introduction of the basic principle of these different methods. A focus is also on the discussion of advantages and limits of the different methods for different applications. And there's many references for further explanation and details. Yeah, I would like to start with the forecasting based on all sky images. Here in this upper graph, you can see an image of an all sky images showing cloud information, which may be used to derive cloud masks, as you can see here in the right graph. And with this, based on this all sky imager, it's possible to predict irradiance with very high temporal resolution, and also to predict irradiance ramps, as you can see here in this lower graph. And yeah, the very special thing of this forecast is the high spatial and temporal resolution. Typical forecast horizons are in the range of 10 to 20 minutes, depending on cloud height and velocity. And the forecasts are for small areas of about 10 times 10 kilometer in the around the sky imager. Sky imager forecasting is quite a new research topic, with a lot of research going on within the IEA PVPS task. And currently there's also a benchmark of all sky imager forecasting methods performed, which will be published later this year. Yeah, next important method is satellite-based forecasts. Satellite images cover large areas, so we can also have prediction for large areas. Forecast horizons are typically several hours ahead. The forecasts are derived by evaluating cloud motions in the satellite images, and because cloud motion is not the only thing influencing cloud development, but there's also cloud dissipation and formation. If we want to look further ahead than several hours, we need to use numerical weather prediction models, which have a full physical model of the atmosphere and may be applied for forecast horizons up to many days ahead. Yeah, and they are also applicable worldwide. In this chapter of the section, we do not only give an introduction to the methods, but we also give a lot of example of operational methods and weather services operating these models, so you can get also some information where to get these irradiance forecasts. Summarizing the physical and empirical solar irradiance forecasting models, we can see here the model sorted or displayed over the forecast horizons on the x-axis and the temporal scale on the y-axis. So we can see every model has its own regime where it's performing good. In addition to these physical and empirical solar irradiance forecasting models, statistical models or machine learning models can be applied to improve and combine the forecasts of the physical models, and this is addressed in the next section of this chapter, which is on irradiance forecasting with machine learning methods. In this chapter, we first have a general introduction, very short, on machine learning models, and then on the application of machine learning models for time series forecasting, and very important, or more important, the combination of physical forecasting models with machine learning methods, which, depending on the community, is referred to as statistical post-processing or also as hybrid models. And these hybrid models are applied, for example, to improve the output of a physical model by reducing systematic forecast errors by training to measurements, also to combine the output of different forecast models, and in this way to optimize the forecast for different horizons. Yeah, machine learning has growing importance in not only in the field but also in the field of irradiance forecasting. So this is why we have a new chapter specifically for that. And here the examples of the application in solar irradiance forecastings are combined with a short general introduction to machine learning. And again, a focus is discussion of advantages and limitations of the different methods. So far for irradiance forecasting. Now I want to come to PV power forecasting. For many applications, the users want directly PV power predictions rather than irradiance predictions. And PV power predictions can be inferred from the irradiance predictions with simulation of PV power plant production. So irradiance predictions are used as input to these models. Then the irradiance on plane of area is modeled, and then PV simulation models can be applied. And again, we have different options how to do this. If we know PV system description with nominal power and tilt and orientation of the system, parametric models can be applied. If we have PV power measurements, we can apply machine learning methods to convert or to train to these power measurements to convert irradiance to PV power. And of course, the two approaches can also be combined to obtain optimized PV power forecasts. In the first part of this chapter, we give an overview of these basic steps and shortly introduce different methods. And in the second part of this section, we focus on the specific challenges for the estimation and forecasting of regional PV power feed-in. Those are challenges here that in many countries, PV power feed-in by many small systems is not measured. So the actual PV power feed-in of all plants is not known. And additionally, there is a challenge that PV system details are also not known for many small systems. And to overcome these challenges, upscaling is applied. And in the second part of this section, we give an overview of different upscaling methods. Yeah, so far for the methods. Now I want to address the point evaluation and uncertainty of irradiance and PV power forecasts. So the questions we address in that chapter is, on the one hand, how to quantify the overall uncertainty of irradiance forecasts. And beyond that, we also look specifically to the question, what has to be considered specifically for irradiance and PV power forecast evaluations. So we start with an introduction to general error measures. We had that in the presentation before also. So statistical error measures that are typically applied are the root mean square error, mean absolute error, but also more detailed measures. Then we also present this concept of skill scores and persistence, which addresses the question if a forecast is better than a trivial reference model. So persistence means we just assume the situation stays as it is, which is a very trivial way of a forecast. And in the context of this IEA task, we have introduced the concept of smart persistence for better accounting the diurnal course of irradiance and also some averaging effects. Yeah, an important part of this evaluation section is also the analysis of forecast errors with respect to solar elevation and cloud conditions. And then I want to highlight two parts of this section. One is analysis of regional forecasts. So it's well known that averaging effects reduce forecast errors for regional forecasts. And yeah, in this section, we look at the quantification of forecast accuracy for regional averages for regions of different size. Here you can see an example plot for this. On the y-axis, we have forecast errors. On the x-axis, you have the surface area of regional forecasts, and we can clearly see that with increasing region size for the two models evaluated here, that forecast error are decreasing and the forecast errors and uncertainty are decreasing. Then I also shortly want to show you the concept of firm solar power forecasts, which is applied as an effective model, can be applied as an effective model benchmark. So the aim of this concept is to evaluate the benefit of forecasts in terms of costs, rather than just applying some statistical error measures. And the concept of firm power forecasts evaluates the costs to convert a given forecast to a firm solar power forecast or to perfect solar forecast. This can be done, for example, by using batteries to compensate for forecast error or by oversizing of PV plants. And here in this graph, you see an example plot of this benchmark for different models here shown here. And we can see here that for different models, the associated costs are quite different. And so you can see that a better forecast can considerably contribute also to reduce costs in operating a PV power plant. Yeah, so far for the forecast evaluation. And finally, I want to introduce a new section on probabilistic solar forecasting. So why is probabilistic solar forecasting important? We have heard before, or we have seen that forecasts as well as models and measurements are inherently uncertain. And if a user knows about the uncertainty of a model, it allows for more informed decision making and allows for better decisions when using these forecasts. And probabilistic forecasts give uncertainty information for each forecast value. So first, I want to show you types of probabilistic forecasts. One type is so-called quantile forecasts. This is illustrated in the upper graph here. Instead of one forecast value, we have a probability distribution of possible values at each time in point. each point in time. And here in this graph, you can see that the distribution of possible values is quite different for different times of the day, and also is quite different for different weather situations. Another type of probabilistic forecasts is ensemble prediction systems, which are based on numerical weather prediction models. This is illustrated in the lower graph here. So instead of running a numerical weather prediction model only once at one time, the numerical weather prediction model is run several times with varying initial conditions. And in that way, an ensemble of possible forecasts is produced. And the spread of these different trajectories of the ensemble then also gives information on forecast accuracy. So probabilistic forecasting is quite a new topic in the context of irradiance and PV power forecasting. And here we give a quite basic introduction in this chapter to the basic principles and methods used for probabilistic forecasting. The second part of the probabilistic forecasting chapter is about verification of probabilistic forecasting. Here the question is addressed how to assess the quality of probabilistic forecasts. And this is quite more complex than for deterministic forecasts, providing just one forecast value, because in addition to the accuracy, reliability is one important additional criterion, and this refers to if the predicted uncertainty corresponds to the real uncertainty of the forecast. So here in this part of the chapter, also a basic introduction to probabilistic forecast verification is given, introducing the concepts and also some frequently used score and diagrams for that. Yeah, I want to come to the summary. The irradiance forecasting chapter gives an overview of different forecasting methods. It introduces basic principles and idea of the different methods, and it gives many references for more detailed information. We have two new sections on forecasting with machine learning and regional PV power forecasting, because of their importance in the field of solar forecasting. A focus in the chapter is also on the discussion of advantages and limitation of different methods for different requirements. We have seen not the same models are good for every forecast horizon, for example. Then we also give recommendations on irradiance forecast evaluation. And finally, the introduction to probabilistic solar forecasting is given. And last, I want to say that in this chapter, the focus for the forecasting part, the focus is on models and uncertainty assessment and on the discussion of the advantages and limitation rather than on products. So different to the other resource products in the forecasting part, we still have no list of forecasting products, but this might be an outlook for the next update of the chapter. And with that, I want to thank you for your attention and all my colleagues again who contributed to that chapter.
Thank you, Elke, for your nice presentation. And now to the final presenter of today is Dr. Robert Holler. Robert Holler has a PhD in energy science and a master's degree in physics. He has specialized in renewable energy, in particular solar and wind energy, and has more than 20 years of professional experience both as a researcher in energy science and atmospheric aerosol physics, as well as a renewable energy project engineer. So Robert, the floor is yours. Please go ahead, and we can see your presentation.
Thank you, Manojit, for the introduction. Good afternoon, everybody. I am presenting to you the chapter 9 of the handbook, which is called Applications for Solar Resource Products. So this chapter is mainly directed towards people who are developing solar projects, engineers, and project managers, so more on the applied side, not that deep scientific as maybe the other chapters. We strongly enlarged this chapter compared to the version 2. So also the number of authors is nearly doubled than before. So coming from different specialities in the solar field. Also, we deeply went into the modeling of PV, so the different models that exist, and yeah, the different types of models I explained, and also topics like aerosol and variability were strongly enlarged. The content of my presentation is today first, what are the different stages of a solar project and what type of solar resource data are applied in these different stages of the project. And then I focus also on how to apply solar resource data to selecting the site. Also talking more about interannual variability and spatial variability of solar data, and finally about statistical assessment and probability of exceedance. There are more topics in the chapter, but because of limited time, I cannot go into all these details. Solar energy. So this chapter covers solar energy projects in general. So as you know, there are different types of solar energy projects. We have on the one hand side photovoltaics, but there's also solar thermal electricity, solar heating applications, water and air applications for solar energy for disinfection, and so on and so on. So there's a variety of types of solar projects, and they might need also different solar resource data. That's the one hand side. So this is what we are also covering in this handbook to say for which kind of solar projects which type of data are needed from the solar resource side. The second thing is what is explained in detail is the stages of a solar project from the very early phase up to feasibility phase, due diligence, and then also in the operational phase, which lasts for 20, 30 years. There is also a different type of need for solar data because the purpose is different. I listed here the types of purposes that people have on solar data. So it can be, for example, for selecting a site, if the site is not yet decided. Can be analysis of a particular PV power plant or solar power plant in general. It can be for engineering purposes, in the engineering phase. Very important, of course, for economical analysis and bankability issues. And then, of course, during the operational phase, solar resource data are important to evaluate the performance of the power plants. I will go in detail in some of these aspects. In the chapter, we explain in detail then distinguishing these phases. Sorry, here's a numbering. I just see the four phases and also the different sizes of the project. What data are needed? For example, if we start with a pre-feasibility and planning phase of a project, there's in a very early phase, maybe the site is not even decided, there will be a difference if you develop a small-scale project, a medium or a large-scale project. So, of course, the larger the project, the more money is involved, the higher is the demand or the need for high-quality data in terms of not only time resolution, but also accuracy of the data. And Then, for example, I also here cannot go in all the details, but you can then see that in the chapter. For example, feasibility phase is very important, but of course, for small scale and medium scale projects, there's usually not a feasibility study done. But of course, for larger projects in the multi-megawatt range, then, for example, in the feasibility phase, typically satellite data are used. Very often, only for very large projects, there are no ground measurements existing during the feasibility phase. In PV, in solar thermal, it's different, but in PV, usually the ground measurements start around when the PV power plant is installed. So for very large systems, but then it's recommended to have at least 1 year of ground measurement data. So when we talk about 100 megawatt and more, then the demand for accuracy is of course higher. Another application is, for example, due diligence and finance of already existing projects, which have maybe a change of investor. Somebody wants to investigate and test the performance of this power plant. So then also there needs to be a technical due diligence where solar resource data are very important. Also, we see here difference between medium and large scale projects. Typically, also satellite data and long-term time series are used. If there is a ground measurement station available for large-scale systems, then of course this is very valuable. Often it is not. And yeah, here we see some more details, as we have also already heard from other speakers today. For example, Albedo soiling measurements are then, of course, very valuable for such a due diligence study. Currently, they are not often existing. It's for older projects. And I will talk then in one of the next slides more about the topic of operation and maintenance and what data are used for running PV solar power projects. We have a flowchart in this chapter where we then describe in more detail how the site selection process works. For example, site has not yet been selected, then typically maps are used. I will also show you later more details about this. If the site has already been selected, then for this particular site, long-term modeling data are usually used. From that, the profitability is calculated. If it's, for example, not profitable, this particular site, then an option could be to maybe go back to this stage and go or search for another site, which is maybe more profitable, or to stop the project development. If the outcome is profitable, then and the decision is to go for plant construction, then often in case of PV, ground measurements start, or if there's a nearby other station which can be used, this is an option. Yeah, and then for, of course, solar thermal power plants, the ground measurements should start earlier, so in the feasibility stage, so in this stage, because the reliability of just satellite data for DNI is less good than for GHI. And then coming to the operational phase, we heard just from Elke Lorenz the topic of forecasting, which is very important for the plant operation, but not only forecasting, also using on-site measurements to determine the performance of the power plant. I will come to that also. So to give you a few examples, what I just said earlier for the site selection process, for example, I took Libya because it has a very beautiful solar radiation distribution. And you can see here there's a large spatial variability of the solar irradiance. And this is GHI for Libya. So it's quite clear that in the southern area, for example, it has a much higher GHI than in the coastal area, and it's of course for a project developer more attractive than maybe to develop it in the south. Of course, there are many other issues. I don't want to go in the detail about the grid and so on. Of course, this can be things like grid connection and other maybe topics like environmental topics at the site or slope terrain issues can be gizmo with a geographic information system analysis can be modeled to narrow down the areas that are possible for projects to develop. So not only using a solar resource map, but also other parameters can be done in a comprehensive GIS analysis. We also described that in the chapter in more detail. Then strongly enlarged is the chapter about variability. So not only what you can see here, the temporal variability. So here we see the interannual and seasonal variability at the site in the United States. You can see here how variable the irradiance is, and on the right-hand side you see the annual variability over a long time period for DNI and GHI for a site in South Africa. So this gives very important information then for when it's coming to bankability and financing issues and risk assessments also, because to know what's the long-term risk, and it's very important to know about the variability. Another issue is spatial variability. Here two examples are shown. This is on a smaller scale for the island of Oahu in Hawaii. For example, for what applications can such a map be used? One thing is, of course, for finding a site where the, for example, GHI is better to develop a project. Or another thing is from seeing the spatial variability, for example, to locate a ground-based measurement station. If you move in the XY direction, how is the GHI variable in this direction? And so if the station is at a certain distance, can be used to evaluate the possibility to use the station. Also, we are talking about or writing about this in detail in the chapter. From the variability, then a statistical assessment and probabilities of exceedance can be calculated. Here some examples are shown. This is from typical PVSys output, where you can see here the repetition function, where the P90, P75, and P50 is calculated from the variability of the resource data. Softwares available currently, commercial software in the photovoltaic business can nowadays easily calculate this probability of exceedance values. Also, what is not so widely known is what you can see here, the different ways of fitting the data. So this is, from my experience, not as widely done yet in projects and not so widely known. So people who are interested in that and see the effect of the fitting way, what effect does it have on this probability of exceedance levels? It's also explained in the chapter.
Robert, you have 1 more minute to finish.
Okay, sorry, I'm talking too long. Thank you. And also here, so it's explained in detail how important it is to calculate these probabilities of exceedance. Then also, of course, very important is not to use only one data source for when you do a solar resource assessment. Use different sources. We show some examples in the chapter. And as I already said, the importance of using solar radiation data for plant operation. So this shows, this graph shows an example where the real data based on measurements on the ground of an operational power plant is compared to modeled data with using a PV modeling software, and comparing the difference of, for example, the performance ratio in this case, which is very important for contractual issues. With for example, an EPC company, which have to prove that the performance ratio is exceeded according to the contract, but also if this contract is fulfilled, also during the long-term operation, to look if the power plant is operating as it should. It's very, very important to have data. And finally, a comment: medium-sized to small size PV systems often do not have measurements, so we also give recommendations on what can then be used instead of that. So with that, I want to close. Thank you very much for the attention, and I also would like to thank my co-authors in this chapter.
Sure. Thanks, Robert. Thank you for your nice presentation. I'll hand it over to Jan Remand. We're nearly running out of time, but we do have a few minutes. Jan, if you have any questions for our panelists, please go ahead.
Okay, thank you, Manojit. Yes, and thank you for the nice presentations and the many nice questions. I have to select a few of them. As Manojit said, we are running out of time, and but I want to prolongate till another 10 minutes. First, a question to Elke Lawrence, because I know she has to leave 17:30 exact. It's a question like this. In the IEA Wind Task 36, a lot of stakeholders ask about evaluation of probabilistic forecasts and ramp forecasts. Can you comment on how the PVPS group is dealing with this? Is it part of the handbook? And if not, are you working on including it? How do PV deal with ramping?
Okay, so for the probabilistic forecast, there is a special part of the handbook now, especially on this probabilistic forecasting. The last section is on that. And it also gives an introduction to the evaluation methods of probabilistic forecasting and applications to example probabilistic solar forecasts. For the ramp forecasting, it's not included in the current version of the handbook, but I think it's could be a good idea to include it to one of the next versions. I know that some colleagues here in my group and also colleagues of the IEA task also work on the topic of ramp forecasting. There was one publication on a temporal distortion index, and there are several publications on ramp forecasting, so we might consider this as an input for the next part of the handbook.
Okay, thank you very much, Elke. I go on to a question for Manojit Sengupta. Prediction in solar systems is very important to do future income or energy production estimations. How would climate change differ these predictions?
Hold on, so you cut off.
Yeah, it's about climate change of the solar radiation.
Okay.
Can we say about this?
Yeah. So normally nowadays, as our projects are like last 25 years or so, But as we are looking at higher reliability of solar systems, and we're thinking solar systems will last 50 years, we have to seriously take the impact of climate change into account. The biggest challenge right now is that the uncertainties are literally swamping the predictions of change within solar radiation, especially because, as most of you realize, that clouds predictions are the highest uncertainty in any climate model. So that is something we are trying to look at using regional climate models and going down to higher resolutions both in time and space. It's ongoing work. There's high uncertainty, so we can't. It's still work in progress. We've written a paper about future systems, but again, the finding was that the uncertainty is drowning out any signal we are seeing. Hopefully that answers your questions. Not doesn't provide any direction, but that's where we are at this point.
Yes, thank you, Manojit. Perhaps to add, there are very few regions where there is a strong signal enough, but most of the regions, they don't show a clear signal. That's less strong than the variations we have. Then there are several questions to Stefan Wilbert. One of them is about the albedo measurements. How do you come to the conclusion to recommend measuring albedo at only 1.5 meter height? How representative is such measurement for a solar field?
Yeah, thank you for the question. This is certainly a difficult discussion, the height of the albedo measurements. We were in the comfortable position that we already have two standards on albedo measurements where this height range between 1.5 and 2 meters is mentioned from IEC and ISO. The reasons why in these standards the conclusion was 1.5 to 2 meters is that you have to maintain the albedo pyranometers, so they cannot be much higher. Of course, if you would go higher, it would be nice. You can cover a bigger ground area that is then contributing to the albedo measurement. But I think it's a logical conclusion to make such a measurement in a height that also allows the daily maintenance or weekly maintenance.
Okay, thank you very much. Then one more question for you. How reliable is to measure soiling efficiency utilizing IV curve tracers?
So if you measure actually at the maximum power point, I think the efficient or the soiling ratio measurement of two different solar modules is a pretty good choice. If you use the IV tracers and actually compare the two IV curves, it's even better. It's only more complex because in the end, to get one result for the soiling ratio, you actually have to evaluate two IV curves and compare them to each other. So I think that's actually a good option. It's really a quite realistic approach for soiling measurement. So I think it's quite reliable to do this.
Okay, thank you. A question to Aaron Hapti. Is he still available? Yes.
Yep.
So please comment on the importance of not mixing standard uncertainty and expanded uncertainty, I guess, to the overall uncertainty.
Yeah, thank you for that question. Yeah, it is an important point. In some cases, I think users of data assume the calibration standard uncertainty, which is provided by manufacturers or calibration service providers, is expanded uncertainty. This is incorrect because, as I mentioned in the steps, calibration is one of the sources of uncertainty. So we need to follow the steps to get to the expanded uncertainty. So understanding the sources of uncertainty is important, then following the steps to get to the expanded uncertainty is the ultimate goal. Thank you.
Thank you. Another question for you concerning the quality control of ground data for FPV. Are there any standards, guidelines, etc. underway?
So I think if I understand it correctly, thank you for the question first. This is for the Odin PV, I think. So I don't know if there is a standard, but I think one thing to check is IEC 61724 is under revision. So I think if there is anything, it would be included there. So if the person who asks, if he can send us the email, then I can connect him to the technical lead for this standard under revision, which is IEC 61724. Thank you.
Yeah, thank you very much. Then a question to Robert Höller. Is it possible to develop a model for site selection? Perhaps a little bit difficult, but a general model to make.
A model, a computer model?
I guess so.
I never thought about it, to be honest. Well, I would not say a computer model, but an approach strategy. Yeah? But a model. How to say, this is a multidimensional process. I think this is difficult because there's so, as I said in my talk, there's so many aspects to make a site selection. It's not only solar resource, there's terrain issues, legal issues, grid issues, and so on. So I think this packing all this in a computer simulation is difficult. As I said, this is a geographic information system approach, which is usually done.
Okay, yeah, thank you. Then a last question for you, and I guess for everybody. Why solar measurements for PV project development should only pay off for sizes around 100 megawatt? Why this threshold and not the smaller ones like 10? Or
towards me is the question?
Yeah, that's the question to you. Yes, about the sizes of where you should start with measurements.
In the development phase.
Yes.
In the development phase. I would say, from experience, I would say double-digit megawatt. So maybe 20, 30 megawatt and more. I would certainly recommend it. It's always a budget question. So how is an investor ready to invest this in the measurements? Certainly recommendable. It is very much recommendable. It is when you, as I said, come to the double-digit megawatts. For smaller projects, often it is not done because of budget restrictions.
Yeah. Okay. Yes. Thank you very much. One question was very often put in the field. That's when it is available, the handbook. And to answer this, I did this already in written, but it will be available end of March till end of April, both first on NREL webpage, then later on also on the IEA PVPS webpage. So I guess there would be many more questions, but time is up and I would like to end this for today. Once again, many thanks to the presenters and many thanks to the persons attending this, up to 290. This is a very high number for our field. I'm very happy with this. And then I'm giving back to Arabella.
Yes, thank you, Jan, and thank you everybody for the excellent presentations. And we've received many, many questions and we've gotten through a few. So thank you also, of course, to the audience for submitting those questions. Now, we also get a frequent question about the webinar recording. Yes, the webinar is being recorded as we speak. and the recording is now being edited by us, and then we will have it online for you in a few days. And to our ICES members, please remember you already have the unlimited access to all past webinar recordings as well as the presentations on our ICES website. So this would be your place to go for any resources that you are looking for. And now, before we end the webinar, there is one more announcement I'd like to make, and that is that ICES very recently launched our call for participation for our 2021 Solar World Congress. It's going to take place online in October of this year. The call for participation is now open, and you can submit both abstracts as well as forum proposals to it. And we are very much looking forward to receiving your submissions. For any questions or more info that you might need, you can go to the homepage. You see the address on the bottom of the screen. And we are looking forward to meeting all of you virtually this time around in October. Okay, and then with that, I think, we from our side at ICES, and we very much appreciate you joining us today. Again, a big thank you to our speakers. If you have any feedback or any questions, you can always reach out to us at public.relations@ices.org. And there's also going to be a little survey following up this webinar, and we issue that so that we can provide you with the best webinars possible. Yep, and I think with that, it's goodbye from my side. Have a good rest of your day, or maybe your day just got started. I'm signing off from Freiburg, Germany, and talk to you soon. Bye.
Bye, and thank you, Arabella, for organizing this.
Yes, thank you, Arabella, and everybody. Goodbye, and have a good day.